Hey, this is part two of a brief series on eigenvalue inequalities, and we're going to look at the next theorem, and it has to do with minimizing and maximizing over sort of a constrained space. And let me show you what I mean here. If A is symmetric, and then we know that it has m eigenvalues, real eigenvalues, and we can order them. And associated with them are eigenvectors. So if we let x sub h equal the first h eigenvectors. So this x is associated with the largest, and this x sub h is associated with the h largest. And then we let y, h, be the last m minus h plus 1 vectors. So this one is associated with the h largest eigenvalue, and this actually is the mth largest, which is actually the smallest in this set. Okay. Notice there's one value that overlaps. Okay. So if we let s sub h be the vector space spanned by this, and t sub h be the vector space spanned by this, and this is for all h 1 through m. Then what we're going to do is show that when we minimize this over all x's in this vector space, which is associated with the span of this, it equals the smallest eigenvalue. And this one follows directly, mainly because the null space of the row space of h plus 1, so is actually the original s of h. Probably won't go into much detail about that, but I'll mention something later in the proof. And then also we're going to find the maximum value of this when we're restricted to the vectors in t sub n, and t sub n was the vector space associated with this, the eigenvectors associated with the last or the smallest eigenvalues. So let's just jump right in on the proof. So here we have the diagonal matrix of the eigenvalues, and let's put the largest first and then the smallest second. That is equal to this x transpose A x, and that's basically by the spectral decomposition theorem. And then the x we can split into x sub h, which would then be the same as this x sub h, and y sub h plus 1, which is this one but h plus 1, and then a, and then that's again just x. When we multiply this out, we get this. Okay, so this matrix is equal to this matrix. So this is 0, this is 0, and this is a diagonal matrix, and this is diagonal. Okay, so we're going to use this piece here. So that says h x sub h transpose A x sub h is equal to just the first diagonal, the first h eigenvalues in a diagonal matrix. And because they're eigenvectors, we're going to make them orthonormal eigenvectors, and so we get the identity matrix. And so let's let x be an element of this vector space, which is the vector space spanned by these x's, the first h eigenvectors. So because it's in an element of s sub h, we know that it can be written as a linear combination of those eigenvectors. Okay. So now when we look at this first quantity that we want to minimize, because X is an element of S sub H, let's just rewrite X as this linear combination here. And then it becomes over the minimization over all Y where it's not equal to 0. And then we know that this piece here is the identity matrix, and this piece here is the diagonal matrix, and this right here is, if we minimize this quantity, we get the smallest eigenvalue, or the smallest value in here. And this is from one of the theorems on part 1 of this series, and you can go back and look at that. And as before, now to do the second piece of this, the null space of this matrix here, Y sub H plus 1 transpose, is actually the S sub H. These two vector spaces, the null space of this is the same as the vector space of this. So what that says is if X is an element of here, it's actually an element of the null space of T sub H plus 1, which says that it must satisfy this condition. And this piece was the second part of what we want to show. So really these two conditions are the same, just said a little bit differently. So now to prove the second piece, we're going to use a similar approach. We're going to let Y sub H, transpose Y is equal to this identity matrix. Now remember that the Y sub H has the eigenvectors X sub H to X sub N. So it's sort of the smallest, they're associated with the M minus H plus 1 smallest eigenvalues. Okay, and then again, this relationship holds that if we take this product, we get a diagonal matrix of the M minus H plus 1 eigenvalues. So these are sort of the smallest of the bunch. So now let's let X be an element of T sub H, which means that we can write it as a linear combination of these vectors associated with Y sub H. And we're doing this because that we're going to maximize this quantity over all vectors in this vector space T sub H. So let's rewrite the X's in terms of linear combinations of the vectors, which is this. Well, this quantity is I, and this quantity here is a diagonal matrix. And then this is maximized by the largest element of this, which is Y sub H. Remember, all the other all the eigenvalues are smaller than that. So this is the maximum. And then again, to prove the second piece of the maximization, if X is an element of this vector space, that's equivalent to being in this null space, which is equivalent to this definition. So therefore, we have proven the theorem. And this is part 2 of the brief series on eigenvector inequalities. I hope you enjoyed it. Like it if you did, and subscribe so you don't miss the next one. Thanks. Bye.